The systematic nomenclature for organic chemistry is a set of logical rules devised by the International Union of Pure and Applied Chemistry to circumvent problems caused by arbitrary names. The rules are mainly aimed at giving an unambiguous name, from which an unambiguous structural formula can be created for each organic compound. To illustrate the systematic nature of the nomenclature rules, consider the compound 4-hydroxy-3-methylpentanol. The name starts with prefixes and designation numbers for substituents, followed by the root name of the parent structure, and ends with the suffix identifying the main functional group. By the end of this video, you should be able to name any organic compound, even if it is the first time you have ever seen the structure. To name a compound, it is vital to first know what homologous series it belongs to. A homologous series is a series of compounds with the same functional group. A functional group is the reactive part of the molecule. The functional group helps to provide the prefix or suffix of the compound name. You also need to be able to identify the longest carbon chain in a compound. This provides the root of the compound name, as well as having the same functional group. All homologous series can be represented by a general formula, differ from their neighbor by Ch2, have physical properties that vary as the molar mass of the compound varies. For introductory level organic chemistry, the key homologous series you need to be aware of are alkanes and cycloalkanes, alkenes and cycloalkenes, carboxylic acids, aldehydes, acyl halides, haloalkanes, alcohols and phenols, benzene derivatives. The main requirements for the name of a chemical compound are 1. It must describe the structure completely, and cannot be identical to the name of any other compound. 2. It must be as brief as possible. 3. Preferably, it will be the only name possible. The systematic procedure for naming organic compounds starts by finding the longest continuous carbon chain containing the principal functional group. The longest continuous carbon chain is called the parent chain. For example, a 3-carbon compound from the alkane homologous series is called propane. A 3-carbon compound belonging to the alcohol homologous series is called 2-propanol, where the number indicates the carbon number where the substituent is attached. A 4-carbon compound belonging to the alkyl halide homologous series is called 2-bromobutane. The alkene homologous series contains double bonds. Because atoms are restricted from rotating around a double bond, there are 2 possible configurations for alkenes. The 2 configurations are cis, meaning on this side, and trans, meaning on the opposite side. If the parent chain is a ring, the prefix cyclo is added to the hydrocarbon name. One exception to the rule is certain rings that have long-established names, such as benzene, oxane, and pyridine. For example, the carboxylic acid with a benzene ring is called benzoic acid. Haloalkanes are named as if the alkane part is the principal functional group, as we will see in a moment. This has to do with functional group priority ranking. For now, it suffices to know the basic steps for naming haloalkanes. Just as with the previous examples, the longest continuous carbon chain is identified, and the carbon atoms are assigned numbers. The main rule to follow here is that as many substituents as possible must have the lowest possible designation number. Then the position of the halogen can be assigned using the numbering system. When there is more than one halogen, they are to be listed in alphabetical order. For the compound 2-bromo-1-chloro-1-fluoropropane, the carbon number 1 was assigned because that end of the molecule has more substituents. The halogens are then listed in alphabetical order. Bromo and chloro are listed before fluoro, because B and C come before F in the alphabet. Alkene names are based on the longest chain containing the double bonds, whether or not it is the longest chain in the molecule. To show where the double bond is, Start numbering the chain from the end closest to the double bond. For the compound 2-butyl-3-methyl-1-heptene, the carbon number 1 was assigned to the end of the molecule that has the double bond. There is a 10-carbon chain, but if we name the compound based on the carbon chain, then the double bond would not be part of the chain, it would be a substituent. After assigning the parent chain, the substituents are listed in alphabetical order. Butyl is listed before methyl, because B comes before M in the alphabet. If there is more than one double bond, use the prefixes di for 2, tri for 3, tetra for 4. For example, 5 carbons in a chain containing 2 double bonds would be a pentadiene. A parent chain may not include both cyclic and non-cyclic components. When both are present, priority must be assigned to one of them. When a ring is present, the parent chain is determined based on the number of carbons. If the ring has more carbons than the chain, then the ring is the parent chain. Take for example, the compound isopropyl cyclohexane. The 6 carbons in the ring are defined as the parent chain, this being a cycloalkane. The root name is cyclohexane. The isopropyl group is treated as a substituent to give the name of the compound, isopropyl cyclohexane. However, the longest continuous carbon chain is the parent chain, provided it has more carbons than the ring. Take for example, the compound 2-cyclohexylheptane. The ring has 6 carbons, and the chain has 7 carbons. In this case, the ring is treated as a substituent to give the name of the compound, 2-cyclohexylheptane. Now it is time to point out a rule that we have been using without even knowing. Consider the 4-carbon alcohol with hydroxyl substituent at position 1. Its name is 1-butanol. If we were to follow a pattern, the haloalkane with similar structure would be called butyl bromide, but this is not the preferred IUPAC name. The haloalkane is called 1-bromobutane. Something seems off, because we have not considered functional group priority. A compound may have multiple functional groups, in which case, the functional group of highest priority becomes the principal functional group and is named in the suffix of the compound name. The lower priority functional groups are named as substituents in the prefixes of the compound name. The priority order of functional groups in IUPAC nomenclature is based on a relative scale, where all functional groups are arranged in decreasing order of preference. There is no standard method to remember the priority of functional groups in IUPAC nomenclature. But there are some patterns in the functional group priority scale. First of all, it seems like functional groups with more bonds to heteroatoms rank higher in the list. For example, the carboxyl groups, with their double bonds to oxygen, have the highest rank. Lower in the list are functional groups where the heteroatom is nitrogen. And even lower in the list we have sulfur. We can conclude that a good start to remembering the priority of functional groups in IUPAC nomenclature is to remember that higher oxidation state has priority over lower oxidation state. Oxygen has priority over nitrogen, and nitrogen has priority over sulfur. We are now ready to revise the IUPAC nomenclature rules to include what we just learned. First, you must find the longest carbon chain containing the functional group with highest priority. This chain determines the parent name of the compound. Change the ending of the parent alkane, alkene, or alkyne to the suffix of the highest priority group, which gives the parent name of the compound. Number the chain from the end closest to the highest priority group. The other groups are named as substituents by using the appropriate prefixes. If a configuration must be assigned, it is written at the beginning of the name. Configuration assignments include Cis and Trans, ntgegen and usamen, ectus and inister, levo and extro. Such configuration assignments are covered later in the video. For now, let's look at the compound 4-oxopentanoic acid. The parent chain has 5 carbons. as in pentane. There are two functional groups, carboxylic acid and ketone. The carboxylic acid is higher in the priority list as compared to the ketone. The carboxylic acid is declared the principal group and the ketone is treated as a substituent. Because the carboxylic acid is the principal group, the carbonyl carbon is labeled as carbon number 1. Using the prefix oxo for ketone at position 4, we get the compound name 4-oxopentanoic acid. Consider the next example. Here we have the longest continuous chain of 9 carbons, and has determined the parent name for this compound is nonane. The question now is, which carbon is number 1? If we start from the right, the substituents have designation numbers 4 and 8. If we start from the left, the substituents have designation numbers 2 and 6. The main rule to follow here is that as many substituents as possible must have the lowest possible designation number. The lowest possible designation number is obtained by starting from the left. Starting from the other end we would get 4-ethyl and 8-methyl, which is incorrect. The compound's name is 6-ethyl-2-methyl nonane. Notice that ethyl goes before methyl in the name, even though 2 comes before 6, because the substituents must be listed in alphabetical order. Next we have 6 carbons in a ring, with 2 substituents. Because the substituents are identical, any of them can get designation number 1. Here we need to use cis and trans notation because the atoms are restricted from rotating around bonds. In order to make the flat structural representation look three-dimensional, we use solid and hashed wedges. A solid wedge indicates the bond or group is projecting out towards the viewer. A hashed wedge indicates the bond or group is receding away from the viewer. The parent name of the compound is cyclohexane. We can also draw cyclohexane in chair configuration. On this type of drawing, 3 carbons project out towards the viewer, and 3 carbons recede away from the viewer. For both methyl groups at positions 1 and 2, on the same side of the ring, one methyl is axial and the other equatorial. The same structure is obtained by inversion of the chair configuration. This compound name is cis-1,2-dimethyl-cyclohexane. For methyl groups at positions 1 and 2, on opposite sides of the ring, both methyl groups are either axial or equatorial. Here we show both methyl groups in axial positions. This compound name is trans-1,2-dimethyl-cyclohexane. Inversion of this chair configuration would switch both methyl groups to equatorial positions, which is the most stable of the 2 configurations. We established that cis and trans molecules are double-bonded, or ring molecules, with labels indicating the relative organization of functional groups. When the groups on either end of a double bond are the same or are structurally similar to each other, it is a simple matter to describe the configuration of the double bond to cis or trans. Take for example, the compound 2-pentene. The parent chain has 5 carbons. The double bond is assigned position 2, and we get the compound name 2-pentene. The double bond divides the molecule in 2 halves, and because rotation is restricted around pi bonds, there's an ethyl and a methyl group on either end of the double bond. If the alkyl groups are on opposite sides, the compound name is trans-2-pentene. If the alkyl groups are on the same side, the compound name is cis-2-pentene. Because these 2 terms describe relative configuration, cis and trans are ambiguous when it is not obvious which substituent on one carbon is similar to a reference substituent on the other. Take for example, an alkene with halogen substituents on both sides of the double bond. In this case, we need to sort them out in a way that will give an absolute stereochemical description. When most of the groups attached to the double bond are not the same, then the IUPAC system of geometric isomers uses the italic letter E for the German word ntgegen, meaning against, or the italic letter Cid for the German word usamen, meaning together. As an example, consider 4 flying aces from World War I. Here we have ranked them based on the number of confirmed victories in combat. Rank 1 goes to Manfred Richthofen from Germany, with 80 confirmed kills. Rank 2 goes to René Funk from France, with 75 confirmed kills. Rank 3 goes to Billy Bishop from Canada, with 72 confirmed kills. And rank 4 goes to Snoopy Brown from the United States of America, who shut down Manfred Richthofen, his only 1 confirmed kill. Suppose we place the flags corresponding to the country of origin for each of these flying aces. In order to determine if the resulting pseudo-compound is ntgegen or usamen, we first divide the double bond in half. On the left of the double bond, Germany has higher rank than the United States of America. On the right of the double bond, France has higher rank than Canada. If the high-ranking member from the left and the high-ranking member from the right are on the opposite side of the double bond, the configuration of the pseudo-compound is ntgegen, as is the case when Germany and France are on opposite sides of the double bond. If the high-ranking member from the left and the high-ranking member from the right are on the same side of the double bond, the configuration of the pseudo-compound is usamen, as is the case when Germany and France are on the same side of the double bond. Just as the example using World War I flying aces, the general approach of the USAID system is to observe the 2 groups at the end of each double bond. Then, analyze that the higher priority group at the one end and the higher priority group at the other end are on the opposite sides or on the same side of the double bond. Priorities for the USAID notation are assigned using the Canning-Gold prolog sequence rules, which are based on atomic number. If isotopes are present, the heaviest isotope is assigned the higher rank. To assign ranks using the Canning-Gold prolog sequence rules, look at the atoms directly attached to the double bond and rank them according to decreasing atomic number. The atom with higher atomic number is assigned the higher rank on each end of the double bond. If both of the high priority atoms are on opposite sides of the double bond, it is designated E for ntgegen. If both of the high priority atoms are on the same side of the double bond, it is designated Cid for usamen. Suppose the groups attached to the double bond are both alkyls. Then we have a tie, because we would be comparing carbon to carbon. If the 2 atoms attached to the double bond are identical, look at the atoms directly attached to the identical atoms in question. Rank these atoms according to decreasing atomic number. Compare the atoms of highest rank in the second round of elimination. If a difference cannot be found, move on to the next, lower ranks. If a difference still cannot be found, look at the atoms directly attached to the atoms of highest rank in the second round of elimination, and repeat the process. In the Canning-Gold prolog sequence rules, multiple bonds are considered equivalent to the same number of single-bonded atoms. For example, a triple bond is considered equivalent to having 3 bonded carbons, and a carbonyl oxygen is considered equivalent to having 2 bonded oxygens. Warning: things just got complicated. We have introduced 2 types of priority. 1. The functional group with highest priority, according to IUPAC ranking, determines the parent name of the compound. 2. The generic group with the highest priority, according to Canning-Gold prolog ranking, determines the configuration or stereochemistry of the compound. For example, consider a compound with a 6-carbon parent chain, containing 2 double bonds. One end of the compound has an acyl chloride functional group. The carbonyl carbon is designated carbon number 1, and the double bonds are designated positions 2 and 4. We put the information together to get the name of the compound, 2,4-hexadiene oil chloride. Then we use the Canning-Gold per log ranking system to assign the absolute configuration of the double bonds. First we assign the configuration of the double bond between carbon 2 and carbon 3. The atoms bound to carbon number 2 are hydrogen and carbon. The highest ranking atom is carbon. The atoms bound to carbon number 3 are hydrogen and carbon. The highest ranking atom is carbon. Because both of the high priority atoms are on opposite sides of the double bond, the configuration between carbon 2 and carbon 3 is ntgegen. Next, we move on to the double bond between carbon 4 and carbon 5. The atoms bound to carbon 4 are hydrogen and carbon. The highest ranking atom is carbon. The atoms bound to carbon 5 are hydrogen and carbon. The highest ranking atom is carbon. Because both of the high priority atoms are on the same side of the double bond, the configuration between carbon 4 and carbon 5 is usamen. The compound name, including absolute configuration, is 2,4-Cid, 2,4-hexadiene oil chloride. Our next example is a compound with a 5-carbon parent chain containing a double bond. The numbering starts from the end closest to the double bond. That is where we get 2-pentene. On the left side, compare hydrogen to carbon. The highest ranking atom is carbon. On the right side, compare carbon to carbon. And we have a tie. To break the tie, compare the atoms attached to the carbons. One of them is attached to 3 hydrogens. The other is attached to 1 carbon and 2 hydrogens. This is the atom that gets the highest ranking because there is a carbon attached. Because both of the high priority atoms are on opposite sides of the double bond, the configuration between carbons 2 and 3 is ntgegen. The methyl group is treated as a substituent. We put the information together to get the name of the compound, E3-methyl-2-pentene. Next we have a compound with a 4-carbon parent chain, containing a double bond, and a hydroxyl group. The numbering starts from the end closest to the hydroxyl group, because the alcohol functional group has higher priority than the double bond. That is where we get 2-butene-1-ol. On the left side of the double bond, compare carbon to carbon, and we have a tie. To break the tie, compare the atoms attached to the carbons. One of them is attached to 3 hydrogens. The other is attached to 1 oxygen and 2 hydrogens. This is the atom that gets the highest ranking because it has an oxygen attached. On the right side, compare hydrogen to carbon. The highest ranking atom is carbon. Because both of the high priority atoms are on the same side of the double bond, the configuration between carbons 2 and 3 is usamen. The methyl group is treated as a substituent. We put the information together to get the name of the compound, Cid2-methyl-2-butene-1-ol. For the compound that was mentioned in our introduction to the ntgegen-usamen system for geometric isomers, carbon number 1 is selected as 2 of substituents listed in alphabetical order. For the compound on the left, compare bromine and iodine. The highest ranking atom is iodine. 2. Compare fluorine and chlorine. The highest ranking atom is chlorine. Because iodine and chlorine are on the same side of the double bond, the configuration is usamen, and the compound name is Cid. 1 bromo, 1 chloro, 2 fluoro, 2 iodoethene. For the compound on the right, iodine and chlorine are on opposite sides of the double bond. The configuration is ntgegen, and the compound name is E. 1 bromo, 1 chloro, 2 fluoro, 2 iodoethene. Our next example is a compound with a 6-carbon parent chain, containing a carboxylic acid functional group, a double bond, and a chlorine atom. The carboxylic acid is designated as the principal functional group, and the carbonyl carbon is designated carbon number 1. In this case, the compound must be named as if you were naming an alkene. Then change the ending to carboxylic acid. From this, we get the compound name 5-chloro, 3-methyl, 3-hexanoic acid. Then we assign the configuration of the double bond between carbons 3 and 4. On the left side, compare hydrogen to carbon. The highest ranking atom is carbon. On the right side, compare carbon to carbon. And we have a tie. To break the tie, compare the atoms attached to the carbons. One of them is attached to 3 hydrogens. The other is attached to 1 carbon and 2 hydrogens. This is the atom that gets the highest ranking because there is a carbon attached. Because both of the high priority atoms are on opposite sides of the double bond, the configuration between carbons 3 and 4 is ntgegen. From this we get the compound name with configuration E5-chloro, 3-methyl, 3-hexanoic acid. We are now taking a break from the ntgegen usamen system for geometric isomers to look at a cyclic compound with a 5-carbon parent chain, containing a ketone functional group and an alcohol functional group. The ketone part is designated as the principal functional group, and the carbonyl carbon is designated carbon number 1. In this case, the compound must be named as if you were naming a cycloalkane. Then change the ending to ketone. From this, we get part of the compound name, cyclopentanone. The alcohol functional group is designated a substituent at carbon 2. From this, we get the complete compound name, dihydroxy, cyclopentanone. Here we have a compound with a 7-carbon parent chain, containing 2 halides and a nitro group. All the groups attached to this compound are very low in the priority list. So this compound is named as an alkane and all the groups attached to it are named as substituents. The carbon numbers are assigned as to have the largest possible number of substituents with the lowest possible designation numbers. From this we get the complete compound name with substituents listed in alphabetical order: 1-bromo, 4-chloro, 3-nitroheptane. Some clarification may be in order before we name the next compound. Carboxylic esters are named as if they were salts, composed of an alkyl cation and a carboxylic acid anion. For example, if ethanol reacts with propanoic acid, the ethanol provides the ethyl part, the propanoic acid provides the propanoate part. The compound name would be ethylpropanoate. If propanol reacts with methanoic acid, the compound name would be propylmethanoate. If methanol reacts with butanoic acid, the compound name would be methylbutanoate. If propanol reacts with ethanoic acid, the compound name would be propylethanoate. Now that we know how to name carboxylic esters, let's take a look at the next compound, which is a carboxylic ester with a thiol functional group. Carboxylic esters have higher priority than thiols. The carboxylic ester is designated as the principal functional group, and the carbonyl carbon is designated carbon number 1. If the compound had no substituents, the name would be methylbutanoate. But there is the thiol substituent. The prefix is mercapto, due to the functional group having the ability to capture mercury and lead. From this, we get the compound name, methyl, for mercapto, butanoate. Certain cyclic compounds have long-established names, such as benzene. For example, this compound is a carboxylic ester. The carboxylic acid part has a benzene ring. This is called benzoic acid. There is also an alcohol group attached to the benzene ring. This will be named as a substituent. With the carboxylic ester designated as the principal functional group, the benzene carbon where the carboxylic acid functional group is attached is designated carbon number 1. The carboxylic acid part of this ester would be dihydroxy, benzoic acid. Combined with the alkyl part, the compound name is methyl, dihydroxybenzoate. Next we have another polysubstitute benzene. All the groups attached to this compound are very low in the priority list. So this compound gets benzene as the main chain name and all the groups attached to it are named as substituents. The carbon numbers are assigned as 2 have the largest possible number of substituents with the lowest possible designation numbers. The compound name is 2-methyl-1,3,5-trinitrobenzene. And this is a polysubstitute benzoic acid. This compound gets benzoic acid as the main chain name and all the other groups attached to it are named as substituents. The benzene carbon with the carboxylic acid group attached to it is designated carbon number 1. Other carbon numbers are assigned as 2 have the largest possible number of substituents with the lowest possible designation numbers. If we were to number the carbons the wrong way, we would get the methyl group at carbon 4 and the bromo at carbon 6. Using the correct numbers, the compound name is 2-bromo-4-methylbenzoic acid.
No me dejes con la duda, esa irónica sonrisa.
¿Qué te pasa a ti que te ve tan sumisa?
Corazón encadenado en la cárcel de tu amor.
¿De qué me hablas? ¿De qué me acusas? Si no hay cadenas entre tú y yo.